Okay, so this particular lesson is about us, as we talked about, building some skills so that we can actually factor and graph polynomial functions, the special ones. So using synthetic division as we review our skills from last day, what we should see is that when we divide, it says use synthetic division to divide. So we remember that we have to have placeholders, and if it didn't go well for you, don't forget that there are 0 x's, so you need to have placeholders. When you divide, you get a division statement that looks like that, and that's great if you want to divide. And you get a remainder of -7. Notice that if you calculate P1, that you get -7, and you wonder, well, what good does that? If, as we talked about, when we factor things, by definition, factors are things that have no remainder, then the fact that you can get the remainder by simply just plugging in the 0 of the divisor is kind of a powerful tool. Some might even call it a remainder theorem, and we could use synthetic division to divide this one as well. Very simple little problem. And when you divide by synthetic division there, again, you get a remainder of -5. That's great. But by simply plugging in P at 2, which is the 0 of the divisor, you get -5 as well. You say. That's important because, as you can see here, completing the following statements, when it's divided by x plus 1, the remainder can be found by simply plugging in -1. When x squared minus 2x minus 5 is divided by x minus 2, the remainder is equal to P at 2. The remainder theorem says that if you want to know what the remainder is, you can divide, and Kevin can work on his long division because that's way cool, but by doing that, you're going to create a lot of work. Right. Okay, and so the remainder theorem says that if you divide by x minus a, you simply just need to plug in a to state. And this is all a proof, and that may or may not interest you. If that helps you sleep at night, then memorize that, but that is not part of what you really need to know, okay? This part here is the heart of what we're doing. So then I ask you to ponder, and you guys will answer, ponder why that's of any use to anybody. Why do we care about the remainder? So I want you to carry on now and read this next, oh, did I skip a page? I did. Okay, so in the example number 1, you guys have done synthetic division. When you do synthetic division, it says, hey, find the remainder using synthetic division. Wonderful. Go through synthetic division just like you've always done, and you will find that you should get a remainder of -12. You are dividing by, in this case, you are dividing by x plus 1. Now, okay, just look at my work and be careful, because remember that I gave you a trick. Your book does this funky thing where when you look at my synthetic division, you guys, you'll notice that I'm not using the trick. I don't like tricks. I'm dividing straight up, but I'm subtracting, okay? So notice that my divisor right here, I put a +1. You decide with practice and so on and get it nailed down, you decide what you're doing. But my divisor is +1 and I subtract all the way through. In the end, we should all have the same, right? The same quotient, right? But the only part that this question asked about was, what is your remainder? When I divided, I found out that my remainder was -12. Okay, I found out that my remainder was -12. In part B, what if you were to have, it says, use the remainder theorem to find the remainder when this is divided by x plus 1. I was just showing you that I did it by synthetic division. It says use remainder theorem to find. So I didn't need to do it with synthetic division, but I did both ways. So I did synthetic and I got -12, and then I simply plugged in -1 and I got -12. Okay. For part, right? For part two, somebody said, well, this is question number 1 and this is question number 2. For part 2, it said that you were dividing by if you were dividing that polynomial, if p at x was divided by, in this case they're dividing by 2x, they were dividing by 2x minus 1, then the 0 for that, when Chris talks about x, the 0 for that is equal to 1/2. So I put 1/2 in there, and I got 39 over 4. Okay. All right. I'm going to pause there, and you guys can now. Okay. So using the remainder theorem, normally you'd have to type all that in there, but in our case, I didn't actually type 1/2 and do it all by hand. I simply used my calculator and I typed the polynomial in there, and I said, well, if I was going to divide by 2x plus 1, what would the remainder theorem require me to try? Instead of doing division, I would simply say, okay, that's my polynomial, and I'm simply going to take 1/2, which is the 0, I'll store that in x, and then I'll substitute that into my function by going back and doing this. Clearly it's 9.75, which is 39 over 4. If you're not sure how to change fractions back into that, you can change it to 39 over 4, okay? So one way would be to go and plug it in there. P at 1/2 is equal to 3 times 6 times 1/2 cubed minus 4 times 1/2 squared and plus 8 times 1/2, and then do this all by hand, plus 6, and that's great, but you're still going to end up with 39 over 4, and it's just nicer for the calculator to do it, because what's going to happen is this isn't going to be the end. You might say, well, what if I divided by, what if my divisor was, what if I said, Max says, you know what, Mr. K, I think that the prime factor of x plus 1 would go in there. Maybe x plus 1 goes in there, so then maybe we even tried that one. I think we did try that one here. So if we said, well, what about x plus 2? Would that work? Maybe x plus 2 works, so I'll plug in minus 2 into there. Whoopsie. My pen. I'll plug in minus 2 and store that in x, and then I'll go back and see, well, would that factor work? Go back and get the polynomial and see what remainder you get with that. Oopsie. Gotta do it one more. There we go. Oh, that one doesn't work either, okay? So the remainder there is minus 74, so that one we're kind of screwed at, okay? All right, carry on to example number 2, okay? Carry on to example number 2. And now notice that Mr. K's division statement, I have a minus 3 because I'm using the normal subtraction method. So if I bring down and I carry on with my work, notice that I boxed in the remainder's got to be 31. It's got to end up with that. And I don't know what this coefficient is, so those are my keys. But I go through my synthetic division and bring down the 2. This is minus 6. That means this is positive 5. That means this is minus 15, so this is positive 15. That means that this is minus 45, so then this right here is minus a plus 45. And that means that this is positive 3a minus 135. And therefore, we end up with 8 minus 3a plus 135 is supposed to be equal to 131. So the puzzle ends up being a equals 4. The other method that they asked you to do, and it's equally fine, I notice I had to change because I forgot to keep it an a, but if you simply plug in and use the remainder theorem, if I plug in 3, if I'm dividing by x minus 3, my 0 is 3, and so therefore my remainder theorem would say, hey, plug in 3 and you should get 131. When you plug in 3, you get an equation that looks like this, which then solves to be a equals 4, and all was good in the land. Okay. Okay. When you continue on, I'm just going to go through I'm going to go through example 3 with you right now, and we'll finish up with the factor theorem. So in example 3, this is how we would expect to see. This would be kind of a long answer question, typical long answer question. And it ends up coming back with that math 10 stuff that we need to know. Okay, so in question number 3, it talks about, hey, I got two things that I'm working on. I'm working on the fact that I know the remainder is minus 41 if I divide by x plus 3, and I know the remainder is 74 when I divide by x minus 2. So in this case, I write those two things, and that's what you should write. That would be worth 1 mark. Simply saying, hey, remainder theorem says when I divide by x plus 3, I get 41. That's what I'm saying right here. But if I divide by x minus 2, I get 74. Remainder theorem again. You have two things you're looking for. You have D and C you're trying to find. Well, use these two rules to see what happens. And you have to be good with exponents and so on. When you plug in -3, you get an equation that looks like that. 162, right? So this is example number 3. 162 minus 27D minus 9C minus 15 minus 8. In the end, that equation simplifies to be 180 equals 27D plus 9C. And the second constraint becomes 8D minus 4C is equal to 40. Okay. You can simplify those two, which I chose to do. Like I can divide this one by 9, which is nice because it's kind of big and bulky. So we'll trim that down. I can divide the other one by 4, and I get 2D minus C equals 10. And what did we learn a couple days ago back in Math 10? I have two unknowns with two equations. I go back to Math 10, and I use a system of equations. Okay. I can use method of elimination or method of substitution, and I need to solve those two. In my case, I chose to use method of elimination. I put them over top of each other. I put number 1 on top, number 2 on the bottom, and I add them together, and it blows up the C's. Once I've blown up the C's, I can solve for D and go back and find out what C is. Okay. And all was good. Factor theorem to me means this. So this is my own words. If you read it and this makes perfect sense, good for you. Factor theorem to me means if I divide 24 by 3, I get no remainder. Therefore, 3 is a factor. It's common sense, right? So the factor theorem is simply saying that I don't want to divide. I know that if I were to divide by x minus a, the remainder theorem says that I can just plug in a. I plug in the 0. But the point is, if you get a remainder of 0, then it's a factor. All right, and that's the important part. So the remainder theorem and the factor theorem really aren't two separate things. They kind of go together like peanut butter and jam. Okay. All right, so in examples 4, 5, and 6, I want you to work your way through that, and I'm going to uncover this as we go and show you the answers because I think now it's time to kind of fly on your own. And I'll uncover it and just talk through each of those examples. Okay, screencasters, you're getting the condensed version. So using synthetic division in question number 4, you get a remainder of 0, but you can also use the factor theorem. In question 5, you are asked to say, well, if somebody was dividing by 3, what would they have been dividing by? X minus 3. And in B, I'm sorry, if somebody was plugging in minus 2/3, they must have been checking about dividing by 3x plus 2. Notice that the factor cannot be written with fractional coefficients. You need to make sure that you do that properly. In question number 6, you are dividing by 2 factors, and so you get 2 factors of x minus 5 and x plus 2, giving you an answer of x squared minus 3x. And lastly, in 7 and 8, you are asked to check those factors, and a remainder of -90 is not good, but a remainder of 0 is, so therefore B is a factor. And lastly, have a look at question 8 and carry on with the assignment. we will talk about number 8